Welcome to this explainer. We're taking those dry, dusty chemistry formulas and translating them into what they really are, the ultimate accounting system of the universe. We're going to move step by step from the everyday measurements you're used to right down to the mind-bending microscopic realm of atoms and molecules. And we'll break it all down so the underlying logic makes absolute perfect sense. Let's just dive right into this massive number out of the gate. 6.023 times 10 to the power of 23. You probably recognize it. It's Avogadro's number. It's here to tease exactly how mind-bogglingly huge the microscopic world actually is. To put that in perspective, if you had this number of marbles, they wouldn't just fill a room. They'd cover the entire surface of the Earth, several miles deep. Crazy, right? But before we figure out how chemists actively use this giant number for everyday lab work, we need to strip things back to the absolute basics of how we measure the material world. So here's our roadmap for this explainer. First, measuring the material world. Second, we'll look at accuracy, precision, and uncertainty. Third, mastering the mole concept. Fourth, understanding equivalent weights. And finally, the science of solutions. Let's get into it. Section 1, measuring the material world and grounding ourselves in the SI units. Think about this. Every single physical quantity in the universe, whether it's velocity, pressure, density, energy, you name it, can be derived from just these 7 foundational base units. It's like the root alphabet of the universe's accounting system. We've got the kilogram for mass, the meter for length, the second for time, the Kelvin for temperature, the ampere for electric current, the candela for luminous intensity, and the mole for the amount of a substance. That's the whole shebang. Now, within these measurements, there's a crucial distinction we really need to nail down: mass versus weight. We swap these terms all the time in everyday conversation, don't we? But in science, they are vastly different beasts. Mass is the actual amount of matter a substance contains. That stays constant everywhere in the universe. But weight is just the force exerted by gravity on that substance. So if you take a chemical sample up to the moon, its mass is exactly the same, but its weight drops dramatically because the gravity is so much weaker. Moving on to Section 2, accuracy, precision, and uncertainty, or as I like to call it, the limits of human measurement. Whenever we measure something, there's always a little uncertainty. And to handle that, we have to entangle two concepts that most people think mean the exact same thing: accuracy and precision. Accuracy is all about hitting the true value. It's dead center of the bullseye. Precision, on the other hand, just means your repeated attempts are grouped tightly together. And here's the catch. They can be grouped tightly together even if they're totally wrong. You can have incredibly precise measurements, but if your instrument is calibrated poorly, well, you're just precisely wrong every single time. This visual perfectly illustrates how this plays out in a real lab. Take a look at student A. Their results are tightly packed right on the true average of 4.00 grams. So they hit the jackpot, both accurate and precise. But then look at student B. Their measurements are really tightly grouped, showing fantastic precision, but they're way off the actual correct value. Good precision, terrible accuracy. Meanwhile, student C has a decent average, but their individual points are scattered all over the place. That's good accuracy, but poor precision. As a scientist, you absolutely need both. So, to actively manage all this measurement uncertainty, chemists use something called significant figures. The basic rule? Non-zero digits always count. They're always significant. But zeros are the trickiest part of the whole system. They only count under very specific rules. For example, zeros sitting to the left of your first non-zero digit are just placeholders, not significant. But if a number ends in a 0 and it's to the right of a decimal point, suddenly it is significant because it tells us exactly how precise the measuring instrument was. Oh, and a quick side note, exact objects, like counting exactly 4 chairs in a room, have infinite significant figures because there's zero uncertainty there. All right, Section 3, mastering the mole concept as we zoom into the microscopic realm. This brings us face to face with a fundamental problem. Chemical reactions happen atom by atom, molecule by molecule. But if atoms are way too small to actually see, how on earth do we count them out to ensure a reaction goes perfectly without, blowing up the lab? The brilliant, elegant solution to that problem is the mole. Just like a baker uses a dozen to mean 12 of something, chemists use a mole to mean 6.023 times 10 to the 23rd of something. It is the ultimate grouping tool. It acts as this perfect, reliable bridge between the unseen microscopic world of atoms and the macroscopic stuff we can actually put on a scale on our desk. Let's see how this bridge works in practice with gram molecular weight. Take oxygen. Its atomic weight is essentially 16, and oxygen gas travels in pairs as O2, right? So its molecular weight is 32. Because of how the mole is defined, this means if we gather exactly Avogadro's number of oxygen molecules, they will weigh exactly 32 grams on a standard scale. Boom, we instantly have a tangible, measurable weight for an unimaginably large, completely invisible amount of gas.
Section 4. Understanding equivalent weights and the reaction ratios.
Okay, so the mole tells us exactly how much stuff we have, but molecules don't always react in simple, neat one-to-one ratios. Imagine a single acid molecule that donates more than one hydrogen atom in a reaction. Comparing it mole for mole with an acid that only donates a single hydrogen atom wouldn't really be a fair fight, would it? It wouldn't balance the accounting books. So, we calculate its equivalent weight. We take the molecular weight of the substance and we divide it by its specific reactive power, like its basicity, which is just the number of replaceable hydrogen atoms it has. This gives us a normalized weight, guaranteeing a perfectly fair one-to-one reaction ratio. And finally, Section 5, the science of solutions. It's time to mix the math. Let's see what happens when we take all these carefully measured quantities, these perfectly balanced moles and equivalents, and mix them into liquids to create chemical solutions. The first major concept we hit is normality, represented by a capital N. It uses those equivalent weights we literally just talked about to tell us exactly how chemically reactive a specific volume of our liquid solution is going to be. Specifically, it's the number of equivalents of a solute present in 1 entire liter of solution.
But wait, normality isn't the only way we measure concentration. We also have molarity and molality. And yeah, those two sound incredibly similar, but their accounting rules are fundamentally different. Molarity, with an R, measures the moles of a solute divided by the total volume of the solution in liters. Molality, with an L, measures the moles of the solute divided by the weight of the solvent in kilograms. So one uses volume and the other uses mass.
So why does that one-letter difference matter so much? It all comes down to the temperature rule. As you probably know, liquids expand when they get hot. Their volume literally increases. Because molarity relies on the volume of the solution, if the temperature goes up, the volume goes up, and your molarity concentration actually drops. But molality relies strictly on mass, the weight in kilograms. And since mass never changes with temperature, your molality stays exactly the same, whether you're working in a freezing cold lab or a boiling hot one. Pretty neat trick, right? We've traveled all the way from the basic kilogram down to the hidden rules of microscopic reactivity. And I want to leave you with this final provocative thought. Now that you understand the mathematical accounting of the universe and how we actually measure it with moles and molarity, just think about this staggering, immense, microscopic numbers hiding inside your everyday life. Every single drop of water you drink, every breath of air you take, operates on a scale so vast it totally defies human intuition. Yet, beautifully, it can all be understood through these basic chemistry concepts. Thanks for hanging out with me for this explainer, and keep questioning the unseen world around you.